Alright, so here we are with a pretty common Newton's second law and third law situation that we study in physics. It's called the Atwood Machine, and this is a simple Atwood machine in the sense that we're going to consider the surface where block 1, so this block here, only has, so the block that is 1.8 kilograms, has no friction between itself and the surface that it's lying on. So this is a fairly simple situation for the Atwood machine. First thing we want to do is sort of look at the individual blocks and do a quick free body diagram just to sort of get an idea of all the forces acting on these two. But then what we're going to do is look at the whole system, that's to say the two blocks and the string, and basically treat it as one body. But for now, let's just look at them individually. This guy on top, I'm going to represent him as a circle, and look at all the forces that are acting on him. There's a force normal from the surface acting up. There's a force of gravity pulling down, and though we said these are not action-reaction pairs, these, because the block is not moving up and down, actually cancel each other out. So we don't really concern ourselves with those. What I am concerned about is the motion to the right, because as the 2.1 kilogram mass is going to fall, it's going to accelerate the top block towards the right. So there's going to be some sort of force of tension that's going to pull this guy off in that direction. And as we said, there's no friction. If there was friction, then there would be a force moving backwards here, but we're going to leave it right now with no friction. Then we have object 2, the one at 2.1 kilograms. If we do a simple body for him, we've got a force of gravity aiming downwards. And we've got, sorry, that's F here, Fg. And then we've got a force of tension acting upwards. And not to scale, but Fg we know is going to be larger than Ft, and that's what's going to pull and accelerate the block downwards. And then according to Newton's third law, and we proved this in class the other day, that the force of tension acting on block 2, that is to say, this component here of force, is going to have the same magnitude, meaning the same amount of force as the one up here. And that's it. So that's the free body for those two diagrams. What I'm going to do now is, the trick is to straighten out the system. So that is to say, I'm going to take the object mass 2 and bring it straight up 90 degrees counterclockwise, so that essentially I have my system, I'm going to draw it over here, that looks like this. So this would be where the pulley would be. I've taken this 2.1 kilogram block and I'm just going to tilt it right up 90 degrees that way. Now, if I do that to the block, I have to do that also to the forces. So that means that my force of gravity is now pointing towards the right. My force of tension on mass 2 is pointing towards the left. So in case you're wondering, again, this is the 2.1 kilogram mass. This is the 1.8 kilogram mass. So this was force of gravity on object 2, so I might want to add a little 2 in there. And then I've got force of tension acting to the left. Our 1.8 kilogram mass, there was only a force of tension acting on this guy, and it was pointing towards the right. I'm going to ignore the up and down y component because it has no bearing on our movement here. At this point, I need to choose a frame of reference that would work for me. In this case, I'd probably choose to the right as being positive. So any force going off to the right, I'm going to consider to be positive. Any force acting on towards the left on this system, I'm going to consider to be negative. So just you're following here, this is force of tension down here. Alright, Newton's third law tells me that based on the string that is not dynamic, that's to say the string is static, it's not moving, so any pulling on one side will have the same force of magnitude at the other end of it. In other words, this force of tension will cancel out because it's in opposite direction to this force of tension here. And all I'm going to be left with is this funny looking force of object 2, gravity. So the force of gravity on object 2 That's the only force here acting on the whole system. That's the force that's pulling the system down, and that should make sense to you intuitively. If you think about it, that's the only force that's acting on this whole system, pulling it downwards, and that's going to pull the box at the top to the right. Alright, now that I've established that, I'm going to treat this as one whole system, one whole object. So the two masses combined and the string combined are one whole object. And if I look at it that way, I'm going to say that it's going to have a net force. So F net, according to Newton's second law, F net equals mass times acceleration. Once again, if I treat this all as one system, the mass that I'm talking about is the total mass, that is to say the 1.8 kilograms plus the 2.1 kilograms times acceleration. That's going to give me the F net. Now, I've done a sort of rough free body diagram for both these forces, and the only force I was left with is the force of gravity on object 2. That is the net force in this system. In other words, my F net, mass total times acceleration, mass total times acceleration is going to equal mass 2 times gravity. That's what the net force is equal to. And if I do this, I plug in some numbers, my mass total is going to be 1.8 kilograms plus 2.1 kilograms times the net acceleration, what the acceleration of the whole system is going to equal the only force that's acting on the system, mass 2.1 kilograms, times the acceleration due to gravity, which we know is 9.8 meters per second squared. So I'm going to do a little calculation here and solve for my acceleration. I see that my acceleration is going to equal, if I plug in the numbers, 5.3 meters per second squared. That means that the whole system is moving at 5.3 meters per second squared, and that should make sense to you that it's less than 9.8. Once again, I explained this in class. If I were to cut the rope of this system right here, the top block wouldn't move. This block here would be in free fall. But in the situation we have right now, the rope is not cut. They're tied together. So the 2.1 kilogram mass is falling, and it would like to fall in free fall at 9.8 meters per second squared, but it's being held back by a mass here at the top, 1.8 kilograms, and that's going to slow down its overall acceleration. The next common question that you would be asked in a Atwood machine system like this would be, okay, now that you've solved for the overall acceleration, what is the tension in the rope? So what is this force of tension that we canceled out here? So I'm going to move on to the next slide and explain to you how we solve for that. Alright, so now that I've solved for the acceleration of the total system, the tricky part is realizing that I have to go back and look at each one of these blocks as individual masses, because each one had a force of tension associated with it, and we know that the force of tension is the same between them, but the point is to try to solve for that magnitude or the value of the force of tension. So what I'm going to do is start off with the block at the very top. I'm going to say that the force of tension, as I see here, is the only force acting on it in the x component. Once again, I've ignored the y components because they just cancel out top and bottom. The normal and the gravity on block 1 at the top here, they cancel out. Gravity, normal force, balance each other. There's no motion in the y component, so I cancel them. I don't even bother thinking about them at this point. So the only force that's acting on him is the force of tension. So that means if this is object 1, for object 1, the only force acting on it, so the net force, is going to equal mass times acceleration, and it's equal to the force of tension. And just so you're kind of following along here, this is mass 1, the object number 1 here. If I plug in those numbers, mass 1 is 1.8 kilograms times the acceleration that we just solved for. We know that this block is going to be accelerating the same rate that the other block is going to be accelerating. They're tied together by a string that doesn't stretch. So it's going to be accelerating by the 5.3 5.3 meters per second squared. This is the acceleration of the system. This is going to equal a force of tension that we're trying to solve for. Not a great color to work with here. Let me try this again. Force of tension that we're trying to solve for. So at this point, I'm going to grab a calculator. I'm going to say 1.8 kilograms times 5.3 meters per second squared. That gives me roughly 9.5 newtons is equal to my force of tension. If you just look at a quick unit analysis here, I'm going to look at kilograms times meters per second squared is equal to the newton. And that's how this becomes a force with a unit of newtons. All right, that's the easy one to solve for force of tension. What if I'm a little bit concerned that my answer might not be correct? Well, to double check, what I'm going to do is do the exact same thing for object number 2. So I'm going to draw a little line here. I'm going to draw for object number 2. Now I'm talking about this box right here, this block hanging off. I'm going to say that the net force, F net for that guy, we said is equal to force of gravity minus the force of friction. Let me explain why. Oh, sorry, force of tension. Sorry, no friction here. No friction yet. Force of tension. Let me explain why I chose this. I know that this box is going to accelerate downwards. That's what we've solved for. So I'm going to set downwards, in this case, as positive. Just like if you look at the first slide, we had set to the right as positive. I straighten out this whole system. While bringing it back down here, that means the bottom is positive. So any force acting downwards will be positive. Any force acting upwards will be negative. And in this case, that means that our force of gravity on this object will be positive. Our force of tension will be negative. And that's how I have it set up here. F net, which is positive, equals Fg, positive, minus Ft, or plus a negative Ft, which will give me a minus Ft. Alright, I'm just going to reorganize this a little bit. So F net, as we know, is mass times acceleration. In this case, mass 2 times acceleration equals Fg is the weight of the object, or mass 2 times gravity, minus the force of tension. I'm going to bring the m2g over to this side of the equal sign. I'm going to have m2a minus m2g equals minus ft. Plug in the numbers here. I have m2 is 2.1 kilograms times the acceleration that I solved for before for the system, 5.3 meters per second squared, minus 2.1 kilograms times 9.8 meters per second squared equals minus ft. Well, that's getting pretty messy. Equals minus ft. If you can make that out, good for you. Alright, the difficult part now is just to grab these numbers, plug them into a calculator. 2.1 times 5.3. Notice the units again, kilograms meters per second squared, that's in newtons. And then over here again, 2.1 kilograms times 9.8 meters per second squared. Notice this is acceleration due to gravity. This is the acceleration of, this is the acceleration of the system. Hope I didn't confuse anybody there. That's a really important concept. As a matter of fact, most mistakes that are done with the Atwood machine happen right here. People aren't too sure what to plug in for A here. So make sure you understand if I'm talking about a net force, if I'm talking about the actual acceleration of the system, I have to use the acceleration we solved for. Alright, long story short, I solve for Ft here. I get negative 9.5 newtons equals a negative Ft. If you just ignore the negative signs or flip each Ft and 9.5 on either side of the equal sign or divide by -1, whatever way you want to do it, these cancel out and you get 9.5 newtons equals force of tension. Does this make sense? Well, have a look. 9.5 newtons up here is what we discovered for the force of tension at the top. 9.5 newtons down here is what we just solved for in a completely different system with the second block. We get the exact same value. Newton's third law works. It's beautiful. And here it is for you. So once again, the simple Atwood machine, no friction at the top. Hope this video makes sense for you.